Good morning, good afternoon, good evening, everyone, wherever in the world you're joining us from. We are happy to have you here with us for this webinar. My name is Emily Hirata, and I'm the Programs Network Technical Assistant, and I work very closely with all of our ADRA Technical Learning Labs. And so I'm very happy to have our Health Technical Learning Lab sharing this webinar with us today. And just before we start, a few housekeeping items as Sahara gets the presentation screen all set up. If you have any technical assistance, any needs for technical assistance, you can't hear the presentation or you can't see it, something like that, feel free to use the chat box to type in any of your issues, and I can communicate with you from there. In terms of questions on the webinar content, please save your questions until the end. There will be a question and answer portion, so you'll be able to ask your questions then. If you have any questions during the presentation, please type them into the chat box, and we can address them afterward in the Q&A. Or if the presenter sees it and decides they want to answer it then, they can do that then, but that's up to them. But we will have the Q&A portion afterward. So I will ask everyone to please mute their microphones so we don't have any echoing or noises that can disrupt the presentation. Just so everyone knows, this webinar will be recorded. So if you need to leave early or if your connection drops, we will be sending out a link later on where you can access the recording. And lastly, we will be sending out a survey as well about the webinar afterwards. So please make note of any special items that you heard today that impacted you in any special way. We would love to hear about that in the survey. So with all of that said, I'm going to hand it over to Jason Brooks to introduce the webinar topic and our presenters. Jason, take it away.
Thank you, everyone, for joining. I'm pleased with what a great representation we have from around the world. And my name is Jason Brooks. I'm the Senior WASH Technical Advisor at ADRA International. And it's my pleasure to introduce this, what may become a series of webinars, depending on your feedback. Our introductory topic is an introduction to groundwater wells and water lifting. And our two main presenters today, which I'm pleased to introduce, are Wernher Reith, Senior WASH Technical Advisor from ADRA Sri Lanka, and Sahara Anae from ADRA New Zealand. She's a program manager. And without further ado, I'm going to hand over to them to start our topic.
Hi, everyone. And kia ora from New Zealand. My name is Sahara Anae, as Jason's introduction. Thank you, Jason, for the introduction, and Emily for organizing and facilitating our presentation. I'm just going to pull up our presentation now for everyone to see. Today, is everyone okay there? Okay. Today we will be presenting on groundwater wells and some subjects around its rehabilitation works. We will be looking briefly into groundwater and its most basic definition. That will be very handy to use and to understand, especially when reviewing projects in this area. We will also be looking at the types of water wells and types of rehabilitation to look out for when supervising rehabilitation works. We will also be looking at safe water sources, focusing on some major microbiological contaminants with emphasis on sanitation, safe transport and storage, and a brief explanation on disinfection and treatment, as well as what to look out for when doing a sanitary inspection. And to finish us off, we will be looking at some primary and important components for a properly constructed well. Ooh, someone's microphone is on. Emily, should I still continue with that noise?
Yes, please continue.
Okay, all right. Sorry about that. What is groundwater? Groundwater is a body of water that is found underground within the earth, in the cracks and spaces in the soil, sand, and rocks. Groundwater is stored in and moves slowly through porous soil, sand, and rocks called aquifers. An aquifer is typically made up of gravel, sand, sandstone, or fractured rocks. The water moves from the surface through the spaces that make them permeable. The speed in which the water moves and groundwater flows depends on the size of the spaces in the soils or the rocks and the connectivity of these spaces. I may have missed out something. And with the replenishment as well, or the groundwater recharge, which can be done by the rain or melting snows that seeps from the surface of the land into the groundwater. In accessing groundwater, groundwater can be accessed by excavation, which is normally done by digging, driving, boring, or drilling. These can be done by either manpower or machines. To get this water from the ground up to the surface, or what we call draw, you can do this either manually, which can be done by pulling bucket, or mechanically done with a pump. Okay, I'll pass this on to Wernher now to give a couple of explanations on the next two slides.
Hi, can everyone hear me? I hope you all can hear me. Hi, I'm Wernher, Reith. I'm the technical specialist for Sri Lanka. And probably, Sahara, keep the slides on the screen. Yes. There are various approaches to identify groundwater. And as most of our field officers, we know that, wash and groundwater is a huge topic to discuss about. But with the limited time that we have, we'll try to give you some explanation and probably, share through emails, whether we have very deep questions. And there are two ways where people use, methods they use to find groundwater. An ancient system was something called water dowsing. But, it's not like very scientifically proven that by dowsing, having a fork stick, you can find groundwater. But this is very effective, especially if you are finding surface water. But most of us who are in WASH and who are used to groundwater, we do a resistivity study. And this is by passing direct electric current of maybe 50 to 40 volts. And through the resistivity readings and the changes in the data, and through identifying the various graphs that are plotted thereafter, we can find out, whether there's availability of groundwater. And as Sahara mentioned earlier, either it could be through a duct well or a tube well or something like that, that we can determine as to what type of well we are going to do. And especially when we are using the resistivity study, Sahara, probably you can switch on to the next slide. When we do resistivity study, basically we will probably determine that we are going to do a tube well or a bore well. right? And through the resistivity study, we will get to know the depth of the well. And therefore, while drilling, it's very important for us to have what type of drilling we are doing, and the time and the date we finish, and the overburden, and the the geology of the area, and the type of sand, mud, or rock that we begin to observe while drilling, because these things are very important for us to basically, as in Sri Lanka, where all this data is sent to the National Water Board, where they keep all this data for future reference, and then they will monitor these wells during drought seasons, how the water table drops, and if there's no proper recharge, then there'll be limitations for the hand pumps that will be installed for these wells. So therefore, a drill log is very important, especially when you are going for a tube well, because that gives you a history of that tube well. Sometimes in projects we drill and we don't have proper data or details, and then we move on, and if there's another project that comes where you need to rehabilitate those hand pumps after so many years, then no one has the data as to see the depth of the well or what yield it has. And so this data is very important when we are extracting groundwater through a tube well. Next slide, Sarah. Okay, there are types of water wells. First is what you find right around the world is the common dug wells, right? And as you see, most of these dug wells are, they're not very expensive, but I know it's sometimes very tired to do a dug well. But there is also a criteria that needs to be followed. For example, in Sri Lanka, we have a standard of between 40 to 50 feet if we are going to do a dug well, right? Because this is to make sure that there are no latrines or septic tanks close by, and through this way, the water could get polluted, right? And for this, of course, you don't need to have an electric pump, but depending on the location, situation, and your need, you can also have a centrifugal pump, an overhead tank, and it will be easy for you to use. And then the other one type of wells are the driven wells. This is where you, in most places where you have, you identify a location, and then with a very hard driven, a metal pole, you keep either, like in Sri Lanka, of course, we use PVC, 1000 types PVC, but I know in some other countries they use a screened or various type of GVC pipe, GI pipes, and what they do is they hammer it into the ground, and until they get a reasonable amount of water, and then to extract that water, you will definitely need a pump to extract that groundwater. And then you find if your dug wells are not properly giving you a good yield, and if it is not possible for you to have a dug well or a driven well, then you go for a drilled or a tube well, right, by using a machine and a compressor. And these, of course, you can achieve up to 450 feet or beyond that, depending on your need and depending on the geology of that particular country. And of course, to bring this, to extract the water from a tube well, you will definitely need a submersible pump. Currently, ADRA Sri Lanka is, we have installed the Grundfos brand pumps, and I think the reference number is somewhere on SQ1, which is a very user-friendly pump. And this pump could be used by either by solar or by electricity or wind, right? So there are various ways you can use this submersible pump. So currently we are experimenting on some of our locations to extract groundwater from the tube wells, right? And you see, even tube wells, there is a criteria that we need, that's around 500 feet between any water source, right? And so this is to make sure that people will not just start putting up hand pumps here and there. In our country, in Sri Lanka, it's the government is a bit strict where how you install a hand pump and where you put it. So you need to make sure that all those data and the information goes to the government. So I'm talking on the context of Sri Lanka. So because we are quite particular on how we preserve the groundwater, right, for the future generation without being contaminated. Because in Sri Lanka, we see that we have the chronic kidney issues, okay, and so people are suspecting it's because of groundwater. So so therefore we have Sri Lanka has brought in various regulations where, you know, people will not overpump, but to, you know, keep the groundwater stabilized for the future generation, right? And I think from next slide onward, I think Sahara will be able to give you some more information about contamination of a bore well and how the water could be contaminated.
Yes, thank you, Wernher, for that. All right, thank you, Wernher, for that. Is everyone still there?
Yes, we can hear you.
So quiet. Okay. All right. Yes, and similarly also, sorry about that. In my experience here in the South Pacific, majority of wells that are within the Pacific are drilled wells as well. And similarly with Sri Lanka, these drilled boreholes need to be at a certain radius from each other. And also it's a precautionary measure put there by the government and the departments of waters as well, to make sure that people are not drilling bores wherever they feel like and over pumping from the same groundwater level or the groundwater source. With contamination of bores or wells, the well water may be contaminated or may contain microorganisms and chemicals that will make you sick. Contaminated well water can cause nausea, diarrhea, vomiting, and potentially lead to serious health problems in the extremes, such as cancer, kidney disorders, and brain damage. Contaminants known as nitrates are especially hazardous for infants because they can disrupt oxygen flow into blood of babies. Water quality of wells should be tested regularly for bacterial and nitrates. And I realize, I think in different parts of the country and different countries, they have different time frames or frequencies in which water testing are done. So this is something that should really be kept a close eye on to ensure that water quality testing are done on a regular basis. Shallow wells are most at risk for bacteria, leading to diarrhea and vomiting. Wells near septic systems and livestock are susceptible to nitrates because they derive from human and animal waste. And the types of testing that you carry out will depend on the country, location, and types of hazards surrounding the bore and or the well. What makes a water source safe? Now, there's various factors that contribute into making water source safe, but we've selected 6 most important ones that we think plays a vital part in this. The first one being the construction of the well or the bore, whether it be a new or a rehabilitated bore or well. This should be done properly. The location of where the well is, whether it's nearby farming areas or residential homes, toilets, septic tanks, and soak pits, and the likes of that. The maintenance of the bore should be done on a regular basis as well, not just for the borehole, but also for its pumping mechanisms to ensure that the pumps are operating properly and at the drawing speed that it's supposed to. The water source and the nature of the aquifer, again, avoiding the overpumping. Usually when a bore is drilled, there is a georesistivity study which measures the depth of the freshwater, groundwater, freshwater aquifer that's that we're trying to draw from the ground. And during the pump testing of this, which is one of the primary tasks that must be done before the actual pump is put in, is very crucial in avoiding that overpumping. Human activities, you must note your surrounding environment for potential issues. And again, with water quality tests, something to be done regularly. For disinfection of water wells, the most common disinfection for wells can be done with chlorine. I can say this especially as well for the South Pacific, for its bores and the quality of water. It might differ again with country to country. It's easy to do disinfection in automated boreholes, again with the chlorine, but this is probably something we can go into detail about in our next webinar, when we start to go a little bit more technical than this. The most difficult disinfection is with a hand-dug well. The quality in a hand-dug well is often very poor due to the construction of the above-ground elements and unhygienic methods of collecting water. For example, the pooling bucket or the rope and bucket that may be used to collect water, and then the rope and bucket are often left on the ground and exposed to disease-causing pathogens. There is often no sanitary seal in hand-dug wells, and the construction of the above-ground parts of the well does not provide adequate protection from intrusion of surface and dirt. Because of the large diameter also of the hand-dug well, it does require much more disinfection to ensure that the water quality is up to standards. For a hand-dug well, the disinfection is a daily thing. At a minimum, the well needs to be disinfected every week or two, and disinfection needs to be performed not only on the water in the well, but also on the well casing. Now, in a hand-dug well, this requires scrubbing the walls, the well casing using a brush or a broom, and a chlorine solution, buckets and ropes, and whatever methods are used to collect the water. All of these things must be disinfected. So for a hand-dug well, not only accessing groundwater is very laborious, the disinfection process as well is quite laborious also. Now we'll move on to components of properly constructing a water well. For each, you'll be seeing the same diagram in the next few slides, but the difference will be where the blue shade that or the blue line that you see here, that demonstrates what I'm talking about. So borehole, for example, just looking at that blue line is what that word is referring to. The borehole should be about 50 mils or 2 inches wider all around than the well casing. This needs to be clear of obstructions all the way down. Now, sometimes when you're drilling, that's not necessarily the case, but again, something a bit more technical that we can cover in the next webinar. And a borehole should be deep enough to reach the lowest expected water level. The casing, as you see, the line is now moving a bit inwards from the previous shade of a borehole. The casing or the lines and walls of bores, and it's often made of PVC pipe. If the borehole is 200 mil or 8 inches, then the well casing should be 2 inches smaller. That is around 100 mil. And this is probably applicable for most bores that I have experience with, where the casing is always 2 inches smaller than the bore diameter. The space between the wall and the casing is 2 inches or 50 mil, all around the casing from the bottom to the top of the bore. The bottom of the well casing is capped and the lower section is slotted. The lower section here is either slotted or it has holes to permit water to pass into the casing. The gravel pack, you will see the gravel pack around this area here. That's a coarse sand or a gravel which fills the 50 mil spacing between the well casing and the wall of the borehole. Fill the space with this unit The filling of the space in this unit is around 1 meter above the pump casing, and the gravel pack allows water to flow from the aquifer into the well. For a pump pad, that's this solid gray color you see up here, is a sanitary seal, and the pump pad stops surface water from contaminating the well. The pump pad is made of concrete and should be thick enough and reinforced with rebar to keep it from cracking. Cracking would allow surface water to seep into the well, which then causes contamination, one of the many ways. The sanitary seal and pump pad. The sanitary seal and the pump pad stop surface water from contaminating the well. Oh, this is probably a repeat of that with a couple more information. The pump is made of concrete and should be thick enough to reinforce that. Yes. The cracking would allow seepage into the well. Yes. And the sanitary seal is made out of slurry or bentonite clay and cement. So you can already tell from the contents of which it's constructed that it's quite a solid structure. Add a layer of clay cuttings and bentonite that have been removed during the drilling process directly on top of the gravel to help seal the gravel pack. Well, this is basically the additional layers that you can put on top of the pump pad, basically when it's finished. Because when you're drilling, you've got pieces of your cuttings that come out from the ground as you're drilling down towards your groundwater. So basically what it's saying is to use those cuttings to layer the top part of that pump pad. And the concept of it all is to really try and stop the outside water or any contamination from entering the bore. I'll hand it now to Wernher again to give a brief explanation of this.
Yes. Hi team once again. Thanks Sarah for that explanation. You have seen the structure or the construction of a hand pump mounted on a tube well. Well, it's not rocket science, but it's something that these are projects that usually face a lot of difficulties around the world. You know, the International Institute of Environment and Development, they say that almost $360 million has been spent on building boreholes, and as a result, you know, you see almost 50,000 of water supply points in Africa are functioning. Like even in Sri Lanka, we have thousands and thousands of hand pumps that are not functioning because some people, they think it's very technical. Some project managers think, oh, it's too technical, we can't handle it. But it's not rocket science. It's very easy. The fact is we need to set up systems and methods. One thing that we follow in Sri Lanka is probably even other countries in Africa and India and Bangladesh also might be doing it. We form a water consumer committee right after the borewell is done. And then we give them a training as to how they need to remove the components of the pump, for example, the bucket washer and the foot valves. And then they can, you know, we also give them spare parts, a 2-year repair kit, right? And then on and off, we basically monitor them till the end of the project. And we have found out that a lot of people are engaged in repairing their own pumps. And also we get the ladies to assist because usually in most places, ladies are the ones who go and fetch water. So we get them also involved in this hand pump repairs. So, you know, it's not a difficult part that, you know, the beneficiaries have to play once they have a hand pump, right? Because the failure is no one knows how to repair it, but it's so simple. Can we go to the next slide, Sarah? Right? You know, you just need a basic knowledge, right? You don't need to, you know, be a real mechanic to do that. I think this is one photo of a hand pump with a huge apron, but I would like to show in the next slide the type of hand pumps that ADRA Sri Lanka is doing or constructing. You will see that we don't install the pump right in the center of the apron. What we have done is we have brought it to the left corner right, depending on the location, or probably we can shift it to the right corner, the apron, and you can see right around the apron there's ample space for people to do their washing and their bathing and so forth. Initially, a lot of NGOs and other private companies, what they do is they put the hand pump right in the center of the apron, and there's no space for people to move around. But with this, we just did some, thinking, and we thought, okay, let's put it into one corner so people will have enough space, because the aprons are not that big, And then we have a 6-foot drain and plus a soak pit. And through the soak pit, we see that, there are a lot of advantages as well, and also disadvantages. When we speak about the vector control, I'll give you more information on that. And Sarah, shall we go to the next slide? Okay, something that we are working very closely with the Sri Lankan government is, as I mentioned to you earlier, Sri Lanka is facing in the north central and in Uva province a lot of patients with chronic kidney disease, and it goes as CKDU. U means unknown, because now the government is trying to find out, is it because of water and so forth. So what the government is doing is they are also mapping all the water points in Sri Lanka, and this is the most common case in Sri Lanka is for hard water. So this is the map of the hard water locations in Sri Lanka, and then you can see the levels at which it is found. And one of the activities of our current project is also to map the current water sources that we are doing, and also submit this to the the water board. So you see, knowing where your well is and knowing the quality of your water by the test. Now earlier Sahara mentioned that there has to be periodical water tests. So during the drought season, sometimes the mineral content in your water varies, and then during the rainy season it varies. So it's good if you can test your water every 6 months, and to see that the people or the beneficiaries living in that particular water point gets proper and good water. Let's go to the next slide, Sarah. And then probably the next slide is about water points and vector control. I think this is one of the biggest issues I think faced everywhere because of dengue and malaria and so forth. But in Sri Lanka, we have a lot of dengue cases because of stagnant water. So what we have thought of improvising in our aprons is we thought of having bigger and deeper soak pits. Because usually most soak pits are around 2.5 to 3 feet deep, but this just gets flooded due to rain or something like that. And so we thought of having bigger and deeper soak pits, and then also having a longer drainage plus but without a soak pit. And probably one thing that we have experimented is having people plant vegetables or fruit trees or whatever from the water that is coming away from the hand pump after use, right? So there are various ways, but you can't control the vector for, 100%, you can't have 100% control, but there are ways where you can minimize it. So these are two areas where we have thought that if we employ a system like this, it will be better. But I think point number 2, longer drainage, is something where we have got successful, because the soak pits anyhow will get stagnant, and the water will just start flowing out of the drains and would return back into the apron. So now most of our hand pumps, as I mentioned, we just have a long drainage, and then we use we tell the beneficiaries they can plant vegetables or whatever, and then the water doesn't get stagnant. Let's go to the next slide. Probably that would be our last slide before the questions are answered. And I know a lot of officers have a lot of challenges. One is because of low government effectiveness. There's no cooperation with the government, and then the NGOs are left to find their own way of dealing matters with water-related issues, and then also the weak private sector, right? But as of late, Sri Lanka, the Sri Lankan private sector has shown some interest in putting up tube and getting tubers renovated for the beneficiaries. I'm not sure as to how it's happening in other parts of the country or the world. And then also conflict and violence. This is also a big challenge that most of the country officers face for WASH projects. And then natural hazards and environmental risks. For example, like some of our tube wells that we did in the eastern part, it's prone to flooding. And when there's flooding, the water can get into the water pump. So what we do is we analyze those areas, we study the topography and pump history and the history of the area. And what we do is we basically raise the hand pump on a platform like maybe around 3 or 4 feet high, and then there's less risk for the hand pump to get contaminated. And then also another challenge that I see is the lack of confidence in country officers. Most of them think, okay, we don't have wash expertise, we don't know how to do this, we don't know how to do that. But the fact is, in the network itself, I think there are a lot of people who can support even by a call. One example is, I think New Zealand was embarking on a project to pump water in Fiji. I think Sahara was involved and Victoria was also involved in that. And then ADRA, New Zealand and the two of us, we coordinated, Sahara and myself, and we introduced a trickle pump. Sahara, remember? Yeah. We introduced a trickle pump, and then it's, we were able to sort that matter. So I think we should have a good database of the WASH people around in the network so that we could share information and probably also share ideas. And I know if there are difficulties one country office is facing, even through an email or on a Skype or whatever, we can share information and help those countries, because it's very expensive to find a private person to come and attend to a particular matter because of budget constraints. But there are these are ways where if we have a good network, we can be our projects worldwide. WASH projects will be a lot productive. So this is something that Sahara and I were able to share within these few moments. But as I mentioned to you, WASH is a huge topic. Probably those of you who want more information, you can probably write to Sahara and me, and we'll be able to give you more information on whatever you require. And so probably this is the end of our presentation, and maybe we can take up the questions, Sahara, if we are ready.
Yeah.
Emily, over to you.
That's right. Over to you, Emily.
Thanks. So we got a few questions in the chat box. We have 3 to start, and I'll just go from the first one down. The first question is, what kind of method do you use for resistivity activity?
Yeah, okay. We use, actually, the instrument that we are using is imported from India, and we use the resistivity method. Is we pass around, we have 5 electrodes, and we pass electricity, as I mentioned to you earlier, around 50 to 40 volts, and then you see we get a particular reading on our machine, and then we now we are using a very basic machine, and then we need to calculate this, and then we need to draw the graphs. So based on the graphs, we are able to determine whether that particular location has good water, or the water is enough, or whether the water is saline. So there are various models of resistivity meters. Depending on your budget, you can probably go to some of these very expensive European models. And but we are, according to our budget strains, we have imported a Indian one, which is good enough, and it serves our purpose. Hello.
Great, thanks. I'll go to the second question now. What happens in cases where the communities are reluctant to use chlorine, which to them they claim it reduces the natural taste of water? Are there other methods to treat water?
Sahara, you'd like to answer that?
Well, I can speak from the South Pacific experience, and there have been a few communities, especially in the rural communities, that did not like the water to be chlorinated. Although we've provided numerous trainings on why it was important to do so. In cases like that, if the community persists that they do not want chlorinated water, what we will normally do is just reduce the dosage of chlorine so that it helps out somewhat with the disinfection process. But to the point where we think that the communities won't be able to smell the smell of chlorine when they are consuming this water. In some cases, it has worked. In other cases, it hasn't, where we then had to stop the chlorination of the bores entirely. And this is not just, with regards to borehole water sources. This is also with our surface water sources as well, where we have this issue. You can't win with everyone, rejecting some of these things. You just have to work with the community, really. If with other types of treatment, we have, well, from my experience in the Pacific, there are treatments such as the slow sand filtration that's used, or that does eliminate a lot of the turbidity and some of the contaminants, but for things like E. coli, it does not solve that problem. So yeah, I think it's just one of those things where you have to speak with the communities and, and hope that they'll be able to accept some of these things.
Yeah.
Hi, this is Jason. I wonder if I could make a little comment about the chlorination. Regarding the acceptability, there have been times in certain countries where the issue was brought up initially, that there was a perception that chlorinated water might not be accepted. But after giving the community an opportunity to sample the water, their resistance to it actually wasn't as high, and we were able to get communities involved with actually doing the testing and the chlorination in some countries, and it actually ended up being a very sustainable way to do it. And when it was community initiated, there was a much higher acceptance, because the issue wasn't only the potential of taste, it was the idea of, what's going on, this, outside entity coming into our community doing this, what are they putting in our water? So I think Sahara's point about community participation is essential. The other thing is that we generally chlorinate water according to WHO standards to 0.3 milligrams per milliliter of water, and that 0.3 milligrams per milliliter is essential for killing absolutely everything. However, as Sahara said, a residual of 0.1 would still be effective against the majority of common waterborne illnesses, and really that's an almost imperceptible level.
Great, thanks, Jason. Next question. Please tell us more about what is suspected in relation to wells and kidney disease of unknown origin.
Maybe Wernher might know this better.
Yeah. Okay. Okay. As of lately, okay, let me go back to 1970s. Okay. When Sri Lanka was experiencing a severe drought, I think this affected most countries in Asia, and Sri Lanka was used to the traditional way of cultivating rice. Okay, and due to this drought, what happened was people, paddy fields were just left isolated, because when you use the traditional way of getting your paddy field started, you need to cut down and thin out the forest and things like that. So with the introduction of glyphosate, what happened was people started to use this as a weedicide, and like within 3 weeks you can get your paddy field in order for you to start to cultivate. So according to research, they have found out that some of these wells, duck wells, but in particular, are having some of these weedicides and pesticides in the water. So they are trying to speculate to see, okay, is it because of the water? And now they are also doing an experiment or testing the water in tube wells, right? And to see whether the water from the tube wells is a cause for the CKDU. That's why they have capital C, capital K, capital D, and a simple U, unknown, right? So now we have found out in Sri Lanka that most part of Sri Lanka, the water is very hard. Okay, it's hard water, and in some areas it is there's a lot of fluoride in the water. But just because you have a little bit of hardness of fluoride, that's not going to cause a huge effect. But now the water board is doing some experiments and some studies to see whether hardness and fluorides together in high contents is responsible for this CKDU issues. Because when you go to see the North Central and the Uva province, where you have a lot of paddy fields and farmers, these are the guys who are getting affected. And some of the challenges, actually now a couple of months back, when I went to one particular government body, they said, no, we are not going to allow you to have or allow you guys to drill because of its groundwater. Then like probably I had to throw back some questions at him, and I said, look, if people don't drink water, still you can have kidney problems. And then people are having hard liquor and so many type of other stuff they take in their system also could have effect on your kidneys. So there is no particular, they have not identified it's because of this, but I think the storm is being swayed towards water, and everyone is suspecting it's because of water. So some of our projects, we are planning to introduce RO filters, things like that, so the people will be comfortable enough to drink the water. But I'm reluctant to say it's because of water, not just because I'm a wash specialist and we are putting up bowels. But the fact is they still haven't found the real cause of it. And I know people are dying by the day because of this CKDU issues, but I know very soon the government is going to find out the reason, because there has been some huge funding from the Australian government, and they are also trying to find causes for this, the reasons for these CKDU issues. But the storm is being swayed towards water. So, but people don't know how it has, how the water has got contaminated and so forth. But definitely, I think in the near future we'll have some result based because on the studies that is being done by so many NGOs and the government body, there might be a result that they will print out soon, or what the real causes are for the CKDU issues.
Yeah, that would be really interesting to find out once they find something.
Yes, definitely. If there are some information that I'm sure like already some information is flowing in, and I would like to share it with our colleagues, and probably they might experience something in their own countries, and I'll definitely share it with the colleagues.
That would be great. Going back to our questions, I'm going to go a little bit out of order with the questions because there's one that sort of goes back to the chlorinated water issue.
Okay.
One of our listeners says, I want to know if Moringa seeds can't be used to purify water in situations where the community does not like chlorinated water.
Sahara?
I am not familiar with the Moringa seeds method, but I could look up some information and probably send some answers through in another time.
This is Jason. I'm familiar with the Moringa seeds, and I can make a quick comment.
Okay.
Moringa seeds are a natural flocculent, and a flocculent is something that causes the biological materials in the water to sort of glom or glue together and then sink. And there are chemical flocculants, there are natural flocculants, and when these when the material sort of sticks together and sinks down, it tends to carry with it particles in the water that could potentially carry microorganisms. But flocculation alone isn't considered sufficient to 100% remove you know, all the risk of microbiological contamination from water. So the other thing is that the quantities required to be able to perform this on a daily basis would probably be very, very high. So there are simple methods that can be used in combination with each other. You know, sedimentation, flocculation, straining of water, and ultimately boiling of water, which unfortunately uses a lot of fuel and energy in contexts where people cannot accept chlorination. However, I would definitely explore the issue of whether or not there's an outright rejection of chlorination, or if perhaps people, if they were able to sample accurately chlorinated water, they might not object so much. The other thing is it's essential to make sure that the source itself is producing microbiologically safe water. And if that's the case, only a very, very, very low level of treatment may be necessary.
Thanks, Jason. Our next question shifts a little bit. Our listener asks, would it be possible for you to speak to water extraction for irrigation, especially in water-distressed areas?
Yeah. Can you come again with the question, Emily? It was not clear.
Yeah, so it says, would it be possible for you to speak to water extraction for irrigation, especially in water-distressed areas?
Yes, it is possible, and this is where resistivity study comes handy, right? And to get a bowel that, for example, is yielding around 40 to 50 liters a minute, and then you can extract the groundwater through a submersible pump using solar, or you can have a wind-driven pump, and then probably have a storage tank made out of ferrocement, and use it for irrigation. But then I'm not talking about irrigation about like 10-15 acres, right? But you know, probably an acre or a couple of home gardens together that will, you know, generate an income to them through the vegetables or whatever they cultivate. It is possible. We have done it. We have done some pilot projects here. It is possible to extract groundwater for drought-stricken areas, but I would always recommend you need to do a resistivity study and not go through, you know, some of the private drillers I know worldwide, they say, okay, you know, I think through according to our experience, there's groundwater here, we did one tube well there, they had enough water. Not according to, you know, the words that they say, but through a proper study, you will be very successful. And that is why you might not go waste.
Thanks, Wernher. Next question. What solution to facilitate pumping for a child if the depth of this pump is 90 meters? What is the solution?
Okay, is the question that was raised, is it for a hand pump?
I'm not sure. It just says for pumping. Let me see. Insa, would you be able to elaborate more on what you mean?
Oh, it's a hand pump. Yes. Okay. Yes, it's a. So his question was, if it's 90 meters, and what benefits it will do for a child, right?
Yeah, what's the solution to facilitate pumping for a child if that's the depth?
Oh, that's a tough question. But I think at that depth, most of the hand pumps, I think the pressure builds up a bit and it's a bit hard, right? But there's a way. What you can do is, now usually the India Mark III has a standard lever, and probably if you extend the lever a bit, that would be a bit easy, right? That would be a bit easy. But something that we discourage in Sri Lanka is, we usually tell the parents, once the hand pump is established, to go with the child and don't send the child to go and fetch the water for you, because I know at certain depths it's very difficult, because the pressure builds up so much. It's very difficult for a child to pump the water, right? Unless you have a longer lever, which is easier. But at that depth, I know it's a bit challenging for little children.
All right, thank you. Next question. In Sri Lanka, do you know how long an India Mark pump stays functional?
Okay, interesting question, because we just concluded a project with UNICEF last month, and we rehabilitated 300 India Mark III and India Mark II hand pumps. And these hand pumps were constructed 30 years ago, and it was still working, right? And probably usually an India Mark III hand pump, if you use it carefully, in the sense, if the material or the construction of the tube well and the hand pump has done properly, at least for 2-3 years, it will run without any problem. But after that, it needs the bucket washers basically, and the footwear washers will have to be replaced, because it is working in a cylinder like a piston and it gets worn out. So some of these tube wells that we repaired were like 30 years old and were still working, but they had done probably around 5 or 6 repairs during this 30 years. And another thing that we found out during this project was they had done ODEX drilling, that is overburden drilling eccentric. What they do is, unlike the PVC that we use nowadays, they would drill with the casing pipe, which is galvanized iron, and they drill it up to the rock and they leave it down there. So now during this project, when we were flushing, we found out that pieces of this galvanized pipe was coming out, because it's 30 years old and it's getting into corrosion. And that is why nowadays drillers, they don't use the galvanized pipes, and we use something called the casing advanced method, where we eliminate mud drilling, and then we keep on drilling with a special casing shoe until you hit the rock and you lay the pipe there. But if the tube well is done properly, at least the India Mark III should work without any problem, at least for 3 years. Over to you, Emily.
All right, thanks. That's all the questions we have. Does anyone else have any additional questions? You can ask them verbally or type them in the chat box.
This is Jason, and I just wanted to make a comment on the question that was raised about kidney disease specifically.
Yes.
And I wanted to just say that it points out something that was highlighted early on in the presentation, is that particularly if you are not a wash or water specialist, and you are interested in getting involved in water supply activities in the country where you work, one of the things that's extremely essential is to become familiar with the water quality issues that generally exist in your context, because most of the issues related to mineral contamination and salinity of groundwater, the mineral being things like fluoride and arsenic, these would be known by the water professionals in country. So if you're in close contact with the water authorities, it's not always essential to test for everything because there are things that just don't exist in some areas. But you should be routinely testing for everything that is a potential, and then reporting those results back to the water authorities, because it's very difficult to say what may be causing a health problem in a certain area. It could be quite localized, related to pesticides used in farming and improperly installed wells, or it could actually be something that's a well-known issue, related to something like fluoride or arsenic. But those are issues that water professionals would already be dealing with and be able to advise you on.
Yeah.
Thanks, Jason. We got another question that came in. It says, when you say the India Mark III lasts for minimum 3 years, what kind of follow-up costs or alternative technology do we have to consider to make it more sustainable?
Well, I think, India Mark III, I'm sure this question is raised because what if we can have this pump running beyond 3 years without a particular repair? But my 9 experience with the 9 years or the experience with India Mark III, you will find at least one repair coming after 3 years. So what I would recommend is, when you are ordering your India Mark III pump, you should also order with the spare parts, especially the bucket washers. These are the ones that will get worn out easily. For example, if you take an engine has probably one or maybe a 4-cylinder engine, right? It has 4 pistons working, which gives power for the engine. And piston itself doesn't run in the bow. The piston has something called piston rings. So it's the rings that are being worn out and not the piston. So that is to protect your piston. So similarly, you have the bucket washers in the cylinder, right? Which works like a piston, like the piston rings. And so due to the friction that is caused between the brass inner wall and the rubber, you see one part of the rubber will get worn off. So it is always advisable to at least order with your hand pump, if you are going to initially install a new hand pump, some spares, right? And the other parts of the hand pump, like the rods and the upper and the lower foot valves and the chain and the handle and all those things, just need regular checking of the nuts and just lubrication of the chain and so forth. But your bucket washers are the first thing that will definitely, first part of the hand pump that will really get worn off. So I don't see how you can have it running for more than probably beyond 3 years. But I think within 3 years, it's for the sustainability of the pump. It is good to do the repair, because how we are going to identify that your pump is not working properly or your bucket washers are gone. When your pump is new, after you yank it once or twice, you see the water just comes out. But you see later on, you got to yank it in the morning, maybe around 5-10 minutes, and there's no water. And then probably after 15 minutes, you see the water will come out, because now that means the foot valves are gone and it is not holding the water pressure up. So then you should identify that there's something wrong with my pump. And most beneficiaries, if they haven't received the training or if they don't have the spare parts, what they'll do is they will abandon the water source and they'll abandon the hand pump and they'll go back to their streams and their lakes and their ponds, and they'll again, go back to their old system after a couple of years. So it's good always to have some spares when you order either the India Mark III or the India Mark II.
Wernher, can I just jump in on what you were saying to sort of clarify? You're saying that the hand pump, as far as what we might say that the metal parts and the risers, they might potentially last up to 30 years with routine maintenance. And the most common elements of routine maintenance are generally these rubber washers or seals or gaskets that are associated with the piston, which is the part that's all the way at the bottom of the well. And if I understand what Wernher is saying, if if the community or if pump technicians are trained to do this routine maintenance, you know, it's like your car. If the oil is changed regularly, the engine will last much longer. You know, and in my experience, it's very, very unfortunate situation if you have people that are not well trained opening up the well. There's a number of different ways that they can damage it, even in some ways that could make it unrepairable. So if maybe the message here is, number one, as Wernher is saying, to make sure that those essential spare parts are available. And number two, to make sure that there are people well trained, knowing what they can repair, and also knowing at what point they need to call a professional to do a more significant repair, or the entire borehole could actually be ruined as a result of, you know, ineffective you know, repair attempts, and people might just return to using their unimproved sources.
Yes, you're right.
All right, thank you both. Anybody else with any other questions? We don't want to leave anybody out. We still have a few more minutes.
Hello.
Yes.
Hello.
Brown.
Hello. Yeah, this is William from Ghana. On the question with regards to moringa seed being used for water purification, I just to indicate that University of Uppsala, together with some other partners, have done some studies. So we can do a session, then assess the outcome of that research. It will inform us of a lot. Yeah, I just want to indicate. Thanks.
Thank
the
you,
University
Dr.
of
Brown.
Uppsala, Sweden.
Yeah, and if Dr. Brown, if you would share the share any links or documents with us, we can distribute them to those who have been on the webinar. I also wanted to make a distinction which maybe wasn't clear before. There are two types of water treatment that are practiced. One is at the source, where you would, for example, do disinfection and chlorinate a well so that all water coming out of a well or borehole had already been treated. And then the other type of water treatment is at the point of use. So you might think of this as being in the home. And I just wanted to make clear that obviously you can't put moringa seeds in a well. It's not for it's not for source treatment. It would only be for in the home for very small quantities of water. And then we can look at the information, the studies that have been done regarding the effectiveness, but it's definitely only for that small scale treatment in the home, and not as a replacement for water point disinfection. But if we get those things from Dr. Brown, we'll share them with anybody that's interested through the Health Technical Learning Lab. And we want to continue to make the Health Technical Learning Lab a way to disseminate information to everyone.
Absolutely, that'd be good.
All right, thank you. We don't have any more questions in the chat box.
Okay.
So, Jason, Wernher, and Sahara, do you have anything final that you would like to add before we close?
This is Jason. I'd just like to say a big thank you to Sahara and Wernher, who are the ones who put the information together, and to Emily for helping with the technical aspects. I'd like to just say I do see some names here that I'm not familiar with. So if there are people who are not connected with the Health Technical Learning Lab, maybe you received this invitation because it was passed on through someone else, I would like to give my email address so that we can be in contact and we can add you to our mailing list. I'm going to put that in the in the chat to everyone. And please feel free to be in contact with comments, further questions, additional topics that you'd like to see webinars on, and also just to get connected with the WASH component of the Health Technical Learning Lab. So I'm sending my email address through the chat. Feel free to use it.
Yeah, and like Wernher said, if there's anybody who wants to get in contact with Wernher or myself directly, please feel free to do so.
Yes.
All right. Thank you all.
I'll put my email on the chat box.
Yes, please add your emails to the chat box. We can also add your emails to the survey that goes out. Just as a reminder for anyone who came after our introduction of the webinar, we will be sending out a survey. So you should be seeing that in your email inbox. And so please give us your input there. We want to know how this webinar has impacted you and anything you would like to learn in the future, whether it's on WASH topics or other technical topics that we do within ADRA. But other than that, okay, everybody has put their email addresses in the chat box now. So other than that, I'd like to say thank you, and we'll see you next time.
Yep. Thanks, everyone, for this time.
Thanks, everyone.
Yeah.
Have a good night for music.
Yeah. Yeah.
Thanks, Emily.
Thank you all. Bye-bye.
Thank you.
Bye-bye.
Thank you. Bye.